Welcome back to The Explainer. Today, we're getting into the weeds of prefrontal cortex measurement using fNIRS. Specifically, we're unpacking a really compelling preprint by Dr. Jerome I. Rotgans. Now, his research tackles a massive methodological headache in applied neuroscience. Namely, how do we standardize functional regions of interest, our ROIs, so that our measurements are theoretically sound and, most importantly, actually reproducible in the real world?
Okay, let's dive right into this. Here is our roadmap for today. We're going to cover 1. The ROI definition challenge. 2. A theory-driven solution. 3. Mapping the prefrontal cortex. 4. Functional connectivity validation. And finally, 5. The results and practical implications.
Starting things off with Section 1, the ROI definition challenge.
So as applied neuroscientists, you already know the struggle here. As our fNIRS devices get more portable and our experiments get more complex, we're faced with this central question. How do we reliably know exactly what we're measuring in real-world applications? I mean, when you have an operator managing high cognitive load in a really complex operational scenario, trying to define an ROI that is both theoretically meaningful and operationally usable is just an immense challenge.
Traditionally, we've leaned pretty heavily on exploratory clustering algorithms, a data-driven approach, that groups channels based on similarity, which we usually observe during passive stimulation or rest states. But there is a huge scientific drawback to doing it that way. It often produces these sample-specific ROI definitions that are just incredibly difficult to reproduce across different studies. So, Dr. Rotgans is proposing a strict shift to a confirmatory approach, basically flipping the script. This means relying on theory first, grounding our ROIs in prior anatomical and cognitive literature so we have a transparent, reproducible starting point that is completely independent of the sample data itself.
So how exactly do we build that reproducible foundation? That brings us to Section 2, a theory-driven solution.
To solve this, Dr. Rotgans developed what he calls a confirmatory ROI library. Scientifically speaking, this is a predefined mapping of specific fNIRS channels to specific functional domains, based entirely on established neuroscience literature. And the absolutely crucial thing to note here is that in this methodology, the channel groupings are strictly defined before any connectivity analysis actually happens.
This library is anchored in 5 key cognitive domains. First up, we've got executive control and adaptability, which are both tied to Brodmann areas 8, 9, and 46 to handle things like decision-making and cognitive flexibility. Then we have strategic planning in BA10, visual attention in BA8, and finally, uncertainty processing, which covers areas 44, 45, and 47 for whenever the brain is dealing with ambiguity.
All right, moving to Section 3, mapping the prefrontal cortex.
Now that we've got the cognitive theories locked down, how does this actually apply to our hardware? Well, this brilliantly illustrates that translation from theory to operational reality. You can see how those 5 theoretical ROIs map directly onto the precise channel layout of the NIRSIT Lite device. It's clustered super logically. Executive control is right there in the center, strategic planning is right below it, and it's flanked by uncertainty processing on the lateral edges. It gives us a highly structured physical map for these abstract cognitive domains.
Now, a quick reality check here to maintain our scientific objectivity. These are device-specific operational definitions. Because they are tied directly to the physical layout of the NIRSIT Lite, this is not just some universal plug-and-play map that you can slap onto any fNIRS device without rigorous adaptation. Which leads us perfectly into Section 4, Functional Connectivity Validation. How do we empirically prove that this device-specific mapping actually holds up when measuring a real functioning brain? Well, the study looked at a really robust sample of 70 datasets. And these were not your typical relaxed passive tests. These were recorded during 2-hour operational scenarios, specifically designed to induce high cognitive load, tasks packed with time-pressured planning and constant monitoring. For the analysis, the researchers focused strictly on oxyhemoglobin, or HPO signals, because it's such a sensitive indicator of task-related hemodynamic activation.
The core methodology for the validation is straightforward but extremely powerful. They basically compared 2 metrics. First, the within ROI correlation, which is the mean of all pairwise correlations among channels grouped in the same predefined ROI. And second, the between ROI correlation, meaning the mean of correlations across channels in completely different predefined ROIs. The scientific logic here is rock solid.
If the theory is right, and these ROIs are internally coherent, then channels inside the same ROI should correlate much more strongly with each other than with channels outside that boundary.
Let's look at the payoff in Section 5, Results and Practical Implications.
We've got the theory, the mapping, and the test. So what did the data actually show? Across all 70 datasets, the results are incredibly clear. The within ROI correlations sit notably higher, hitting a median of 0.45 compared to the between ROI median of 0.32. This data strongly supports the internal coherence of these predefined ROIs. In short, the channels we group together by theory are actually behaving together in practice.
Let's break down those exact statistics for a second. The mean within ROI correlation was 0.46 compared to 0.33 for the between ROI correlation. That gives us a difference of 0.13. Now, I know what you might be thinking. An absolute correlation of 0.46 sounds pretty moderate, right? But honestly, that is entirely expected in noisy real-world fNIRS recordings where physiological noise and task variability are just inevitable. And despite that noise, the difference is highly significant, with a p-value of less than 0.0001.
Now, what's really interesting about this isn't just the p-value, it's the effect size. They calculated a Cohen's d of 1.91, which is a massive effect. Scientifically speaking, this confirms that the difference isn't just some statistical artifact born from having a large sample size. It is a practically meaningful, substantial difference in how functional connectivity behaves inside versus outside these theoretical boundaries.
Of course, to keep things strictly scientific, we absolutely have to talk limitations. As we touched on earlier, this is validated only for the NIRSIT Lite configuration. It's based entirely on prefrontal oxyhemoglobin connectivity. It absolutely does not replace anatomical co-registration or whole brain imaging techniques like fMRI. And most importantly, while strong within ROI connectivity supports functional coherence, it doesn't definitively guarantee that each grouping uniquely measures one and only one cognitive construct.
I love how Dr. Rotgans sums up the ultimate value of this research in the paper's conclusion. He states, "The library can serve as a transparent and reproducible starting point for applied fNIRS analyses in operational and high cognitive load contexts." This work successively moves the needle for us. It takes us away from data-driven guesswork and points us toward a highly structured, confirmatory methodology.
So, here is my final question to you. As mobile neuroimaging technologies rapidly expand out of the lab and into the field, how could integrating these device-specific, theory-driven mappings finally standardize real-world neuroergonomic research? Because knowing precisely which ROI we are measuring is the fundamental first step to truly understanding the applied human brain. Thank you so much for joining me for this explainer, and as always, keep learning.